This video will be more examples of solving systems of equations using elimination. So in example number 1, we look at the two problems that are there. We recognize that graphing them would be pretty difficult, or solving using substitution would be difficult because there's no variable, neither x nor y, in either equation that is isolated. So we're going to use elimination. We notice that all of our values are already stacked up. So the x's are on top of x's, the y's are on top of y's, and the constants are on top of constants. And in this situation, we're good to go because in this yellow highlighted area, the x's will eliminate if I just add those columns. So if I go ahead and add the yellow column, these things eliminate and I get 0. If I add the green column, I get 9y. And if I add the pink column, I get 18. Now I can go ahead and solve for y because I only have one variable. Divide by 9 on both sides, and I get y equals 2. Then to complete the problem, I'm going to plug 2 into either of the equations. It doesn't matter which one. I'll pick the one that I think is easier. Usually that's the one with smaller numbers or positive values. So I'm going to go with the first equation. That means we have 3x plus 4, and instead of y, I'm going to write 2 equals 8. So 3x plus 8 equals 8. Subtract the 8 to the other side to isolate the x, and divide by 3 on both sides, continuing to isolate x, and you get x equals 0. And then your final answer would be the coordinate pair 0, 2, because x's come first and y's come second. All right, let's do a second example. In our second example, again, we have a system of equations. We have, they're both in standard form. It would not be easy to graph them, nor do we have graph paper. And using substitution doesn't really work because, again, none of the variables, neither the x's nor the y's in either equation are actually isolated. But what we do notice is that, again, our x's are already stacked on top of each other, the y's are already stacked on top of each other, and our constants are already stacked on top of each other. The issue this time, however, is that if we added the stacks, if we add those columns, nothing eliminates because we don't have opposite coefficients. So this time we're actually going to subtract. So if we're going to go through and change all of the signs in that second equation so that we're subtracting. Or you can think of it as I multiplied that second equation by -1. But now, when I subtract, I have 5x minus 7x, which is -2x. I have 6y minus 6y, which is 0. And then I have 4 minus 8, which is -4. So I isolate the x by dividing by -2 on both sides, and I get x equals +2. Then, again, I need to plug it back in order to solve for the rest of the solution. I'm just going to plug it into the first equation. So we add up 5, but I'm going to substitute in 2 for x, plus 6y equals 4. So I have 10 plus 6y equals 4. I'm going to subtract 10 from both sides to isolate the 6y. So I have 6y equals -6. Then continuing to isolate and solve for y, I'm going to divide by 6 on both sides, and I get y equals -1. So I finish it by putting my final answer as a coordinate pair to -1. All right, and example number 3, here we go. So in example number 3, when I look at them, our variables, we have two equations, and we want to solve for both variables. So we want to find the solution. Graphing would be hard. Nothing is has a coefficient of 1, so rearranging to substitute wouldn't be great either. And note that my x's are not stacked on top of each other. My y's are not stacked on top of each other. So the first thing I'm going to do is I'm going to rearrange the equations so that everything is in order and stackable, I guess. So I'm going to leave the first equation the way that it is. 9x minus 3y equals 18. In the second equation, I'm going to bring the negative 7x to this side of the equation by adding 7x. So now I have 7x plus 3y equals 30. Cool. So x's are stacked, y's are stacked, constants are stacked. I note that my y values have opposite coefficients, a -3 and a +3. So if I add, they will eliminate. So I add 9 and 7x, and I get 16x. 3y and 3y gives me 0. And then 18 and 30 gives me 48. To solve for x, I divide by 16 on both sides, and I get x equals 3. Then I need to plug it back in. I'm just going to use that first equation, so 9, and I'm going to replace the x with 3, minus 3y equals 18. And then I will solve, so 27 minus 3y equals 18. I'm going to subtract 27 to the other side. So negative 3y equals -9. And then continuing to solve for y, divide by -3 on both sides, and I get y equals +3. So my final solution is going to be 3, 3. In case you wanted to know how to check things, if you ever want to know if you got it right, you can take your coordinate pair and substitute it into both of the equations in order to see if it in fact works. So for example, I would do 9 times 3 minus 3 times 3 equals 18, and I have 27 minus 9. That does in fact equal 18, so it works in that equation. And then I can put in the second equation, 3 times 3 equals -7 times 3 plus 30, and I get 9 equals -21 plus 30, which would equal 9, so those both work, and that way I know my solution is correct. That's how you solve for a system of equations using elimination.